this video, we are going to discuss imine formation. Now, if you take an aldehyde or ketone and you react with the primary amine under mild acidic conditions, we are going to generate an imine functional group. And your imine is best visualized and characterized by a carbon-nitrogen double bond. Okay, and then you'll notice that the R group, the alkyl group from your primary amine, will then be coming off your nitrogen atom. So before we get into the mechanism, let's look at this breakdown here. You could also form an imine by reacting with NH3, although instead of having an alkyl group off the nitrogen, you would still have one of the hydrogens from NH3. If you react with your primary amine, you will form an imine functional group, in which case we have our carbon-nitrogen double bond, and your alkyl group will still be coming off your nitrogen atom. In the next video, we'll talk about reacting with a secondary amine, where there's two R groups. That will generate an N-amine, and we'll devote a whole video to that. But the N-amine is essentially an amine on an alkene pi bond. And then if you happen to start with a tertiary amine, an amine that had 3 carbon connections and no hydrogens, there would be no net reaction. Okay, this right here is an important little breakdown, because when you're reacting an amine species with an aldehyde or ketone, you want to characterize the amine species right away, and then you know the exact outcome that you're going to get, and that will help as you visualize the outcome. Now, conceptually, we need to have mild acidic conditions to help drive out a water-leaving group. And the mechanism of imine formation is identical to that of the mechanism of N-amine formation up until the very last step at the iminium-ion intermediate. And when we generate an imine, no alpha hydrogen is required, and we can alleviate the positive charge on the iminium-ion intermediate through direct deprotonation of that nitrogen atom. Okay, we'll come back and just accentuate these two ideas when we get to N-amine formation as well. All right. So tracking with you, we are going to react ethylamine and trace acid with this ketone. To visualize the net result, what I would do is say, because I'm reacting with the primary amine, I'm going to generate an imine. Instead of having a C double bond O, we'll have a carbon-nitrogen double bond, and then the nitrogen will still possess off of it its alkyl group. That is the visualization for the net result as we form our imine. Make our carbon-nitrogen double bond where the carbon-oxygen double bond was. The nitrogen will still have its alkyl group coming off. From a mechanistic standpoint, even though we're under mild acidic conditions, because the amine nucleophile is a good nucleophile, it will attack the carbonyl-carbon right away and break the pi bond. Very important conceptual note: do not protonate first. Do not protonate the C double bond O first. Okay, we do not do that. Not an imine or N-amine formation. Because we have a good nucleophile, we attack right away. A lot of people screw that up. Do not protonate first, even though we're under acidic conditions here. Do not protonate first. Attack right away. That then creates the tetrahedral structure with an O minus and an N positive, and we eventually want to get to this intermediate here, which is called a hemi-aminal, which we have a neutral OH and a neutral nitrogen, which means that we have to do 2 proton transfers to make the oxygen neutral and to make the nitrogen neutral. And these 2 steps could be interchangeable. Okay, what we need to do is protonate the oxygen atom to make it into a neutral OH, and then we need to deprotonate the nitrogen atom to alleviate its positive charge. And those steps are interchangeable, meaning you could have first deprotonated the nitrogen atom and then protonated the oxygen atom. Okay, so steps here, you can interchange those. But we need to protonate the oxygen and we need to deprotonate the nitrogen atom to get to the hemiaminal intermediate. And then you need to conceptualize of creating a water-leaving group. And then we kick out the water-leaving group in the next step with the nitrogen's lone pair. The nitrogen collapses its lone pair, forming a pi bond. And we expel in step 5 a water-leaving group. That forms an important mechanistic intermediate for us, which we call the iminium ion. Here there's a carbon-nitrogen pi bond, and the nitrogen is charged positively. Now, because we started off with a primary amine at the stage of forming the iminium ion, there's a hydrogen on the nitrogen, and so we can get rid of the positive charge on that nitrogen by simply deprotonating the nitrogen atom of your iminium ion. Nothing fancy, right? Simple deprotonation of that nitrogen atom. Okay. We'll see that this last step is where imine and enamine mechanisms diverge. To recap that mechanism, because I have a good nucleophile, I'm going to attack right away. I don't protonate the carbonyl first, I attack right away. We then need to protonate our oxygen atom, making it into a neutral OH component. We then need to deprotonate the nitrogen atom, forming a neutral nitrogen component. That forms what's called a hemiaminal intermediate. From there, we need to protonate the OH component once more to form a water leaving group. And then we will collapse in step 5, a lone pair from our neutral nitrogen component, forming a carbon-nitrogen pi bond. And we kick out the water leaving group. Okay, that's our last mechanistic intermediate. And if we began with a primary amine, we can alleviate the charge on that iminium ion nitrogen by directly deprotonating the nitrogen atom. And that would form your imine product. Okay. Now, looking at these two examples here, we're forming imine-like outcomes. I can kind of treat this like a primary amine, and then the OH is kind of like its R group. Or in this case, I can treat that like a primary nitrogen, and this as its R group. So if I were to react with NH2OH, I'm going to form an imine-like outcome, and the OH is just coming off my nitrogen as a substituent. That's called an oxime. Oxime. And if I were to react with NH2NH2 and trace acid, I'm going to treat one of those as my primary nitrogens, and that is the R group. I form an imine-like derivative, which is called hydrazone. Now, right now you might be thinking, hey, wait a second. Wasn't NH2NH2 used in the Wolff-Kishner? And the answer is yes, it was. But remember, when you did the Wolff-Kishner was reacting with NH2NH2, KOH, and heat. So if I were to react with NH2NH2, KOH, and heat, the net result is I just reduce the carbonyl. I add 2 hydrogens and I get an alkane carbon. That is the Wolff-Kishner. The Wolff-Kishner is occurring under basic conditions. Okay, but if you're reacting with NH2NH2 and trace acid, we will have this imine-like outcome form where the nitrogen double bonds to the former carbonyl position and the other NH2 is hanging off as a substituent of the nitrogen atom. Okay, now technically in the Wolff-Kishner, we do generate that hydrazone intermediate. Okay, we form that as an intermediate, but then a bunch of steps take place, which you don't need to know the mechanism for. But we end up kicking off those nitrogens as a nitrogen gas leaving group and reducing the carbon entirely. But this is an important distinction because a lot of students mess this up. On the exam, they'll get NH2 and trace acid and accidentally execute the Wolff-Kishner. If we're reacting under acidic conditions, our orientation should be imine/enamine formation with our aldehydes and ketones. We would only execute the Wolff-Kishner if we're reacting NH2 with KOH and heat. All right, subtle distinction, but I think that's really, really important. So recapping this, imine formation occurs with a primary amine, or we could technically form one with NH3, but then the nitrogen would just have a hydrogen coming off. Secondary amines form enamines, and tertiary amines have no net reaction at the carbonyl carbon. Mechanistically, we attack right away. Do not protonate the carbonyl oxygen first. Attack right away. That nitrogen is a good nucleophile. We need to then generate the hemiaminal, so 2 proton transfers are required. We'll eliminate a water leaving group, and in the last step, we deprotonate the nitrogen atom directly to alleviate the charge on our iminium ion intermediate.